Hey there, let's cover section 3.1. This is straight from your guided notes. Let me see if I'm trying something different today. So it's been a while since I've had to do this. So from the beginning, my pen is not always the best writer, and I'm blaming the pen and not myself. So a relation is a set of ordered pairs. Okay, so we've got like an X and a Y. It's an ordered pair. In parentheses with a comma, that's an ordered pair. And a relation is a set of ordered pairs. So it's not just one, it's multiple sets, multiple groups. The set of the first component of each ordered pair, which is where the X is located, is called the domain. Okay, so domain. This is where the X is located in the ordered pair. All right. The set of the second components of each ordered pair is called the range. Okay, that is your output. And in this case, it's your Y. All right. So let's look at several relations here. A relation is a function. Okay. If each input has one and only one output. Okay. If a relation is a function, if for each of these P, Qs, and Rs, P only has one it goes to, Q only has one it goes to, and R only has one it goes to. A relation is a function again. If P is only going to 1, Q is only going to 1, and R is only going to 1. It's not the other way around. All right. So here's where relation is not a function. So it's not a function because it's not because P is going to X, it's because Q has two answers, and that is not a function. All right, determining if menu price lists are functions. The coffee shop menu shown below consists of items and their prices. Is price a function of the item? Well, that means the function of the item is equal to price. Is that a function? Well, if the input is the item, does each item have its own individual price? Yes, it does. So yes, price is a function of the item. Now they're wanting us to flip it around. Is the item a function of the price? So now we're looking at price and ensure that it only has one item. Well, $1.49 just goes to plain donut. Cool. $1.99, however, goes to both jelly and chocolate donuts. So no, the function of price equals item is not a function. Okay. A function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. The input values make up the domain, that's your X values, and the output or the Y values make up your range. All right, determining if class grade rules are functions. In a particular math class, the overall percent grade corresponds to a grade point average. Is grade point average a function of the percent grade? Well, we're going to go function of percent grade. So function of percent grade equal to the GPA. So we have to look at the percent grade. Does each of the percent grades have their own GPA? Yeah, they do. So if you're between 0 and 56, it's a 0.0. 67 to 71, 2.0. It's not going to two different ones. Okay. So now so that one's a yes. Yippers. Then the next one is asking us, is the percent grade a function of the GPA? So function of GPA equal to percent grade. Well, now we have to look at the GPAs. So does 1.5 only have 1% grade? Well, I'm looking at 1.5, and we could easily have 62, 63, 64, 65, or 66. So no, the GPA, the function of GPA equal to percent grade is not a function. So no, because there's more than one output. Function notation. You've seen this before. So y equals f of x. That's all this is representing here. This is not f times x. Please be careful. I'm still having this conversation. This is just read that y is a function of x. The letter x is representing the input. The letter y or the f of x is representing the output. So depending upon what x is, will make the decision of y or f of x is. It's not f times x. All right, so using function notation for days in a month. Use function notation to represent a function whose input is the name of the month and output is the number of days in that month. Assume the domain does not include leap years. Okay, so I was born in June. We'll just use that one. The function of June, because they're asking us to function notation for days in a month. Function notation represents the function of the input of the name of the month, so function of June. And the output is how many days are there in that month? Well, there's 30 days in the month of June. So for each January, February, March, April, May, all of them through December, with the exception of leap year, okay, we'll have that conversation here in a second. Each one of them would have their own days. All right, but if we went function of days equal to month, that is not a function, because I could say, all right, 30 days. How many months have 30 days? If there's only one, then we're golden and it's a function. If there's more than one, 30 days has September, April, June. Nope, not a function. So, and February is not a function if you do consider leap year. Okay. Interpreting function notation. A function n equals f of y, and they're using a different term now, gives the number of police officers in a town in the year y. What does f of 2005 equal 300 represent? Well, they're giving us all the definitions for how we need to interpret this. All right, the first thing we need to do is see that, let me find out what my thing is, f of y, where y means the year, and the 300 is our n. It's the number of police officers, because the entire function f of 2005 is going to be the number of police officers. So I'm going to write, in 2005, there were 300 police officers. Oh, this pen's writing great. In a town. And that's it. Okay. Identifying tables that represent functions. So we've got our inputs. I'm looking at just the first one that has the 3 inputs and 3 outputs. So each of my inputs has to have one and only one output in order to be a function. 2 only goes to 1. 5 only goes to 3. 8 only goes to 6. Function. Rock on. The next one, -3 goes to 5. 0 goes to 1. 4 goes to 5. Yep, function. Doesn't matter that -3 and 4 both go to 5, because the inputs are -3 and 4. Each of those have to have their own individual outputs as they do. Now let's go to table 7. 1 is not our issue. Goes to 0, awesome. Here's the problem. 5 has 2 outputs. Cannot have that to be a function, not a function. Each input has to have one and only one output in order to be a function. All right, finding input and output values of a function. So I'm going to do this on several slides. Apparently, I think I only made 3 slides, so I'm going to have to put 2 in A and 1. So let's start with evaluate the function f of x is equal to x squared plus 3x minus 4. That's for A. We're just going to take that 2 and plug it in for x. So everywhere there's an x, I'm going to put a 2. Please ensure that you're putting it in parentheses, because if you're not and there's a negative, inevitably people mess up. So just be careful. So this just means the function with an input of 2. Let's say I got 4 plus 6 minus 4. So the function at 2 is just 6. There's our first one. Let's go to B. B is just taking function of A, and that's equal to a squared plus 3a minus 4. I did not put those in parentheses because I wasn't going to have to do anything other than switching out my x and my a. There's not going to be any combinations or of condensing at all. All right, I'm going to go to f of a plus h now. So f of a plus h is equal to, everywhere there's an x, I'm going to put a plus h. So a plus h squared plus 3 times a plus h, and then minus 4. Now we're going to just take the a plus h times a plus h. So that's a squared plus 2ah plus h squared. Now I'm going to distribute my 3 over my binomial. So that's 3a plus 3h, and then minus 4. Can we combine anything? I don't see anything that can be tightened up. All right, let's go to the last one. Now we're going to evaluate f of a plus h minus f of a, all of that divided by h. All right, we've already figured these out. I'm going to have to redo my f of a plus h because I don't remember. So f of a plus h is equal to a plus h squared plus 3a plus h minus 4. Plus 3a plus 3h minus 4. All right, so that's my f of a plus h minus the same function with a representing where x is, and then all of that will be divided by h. So I'm going to give you a little tip here of things that people tend to mess up on when they're doing this problem. Oh gosh, let me see if I can get rid of this. All right, so f of a plus h, which is this spiel right here. So I'm going to rewrite it over here, give myself some more room. A squared plus 2ah plus h squared plus 3a plus 3h minus 4 minus, that is this part right here, minus f of a squared plus 3a minus 4. And all of that is divided by h. All right, first thing I need to do is distribute that negative and change all these signs inside this trinomial. So a squared plus 2ah plus h squared plus 3a plus 3h minus 4 minus a squared plus, oh, nope, hold on. Where is my, there it is, eraser. All right. Okay, sorry about that, minus 3a plus 4, and all of that is divided by h. Combine like terms, so the a squares are gone, the 3a's are gone, and the 4's are gone. We're left with 2ah plus h squared plus 3h, all of that divided by h. I'm going to factor out an h on the numerator, and when I do that, I'm left with 2a plus h plus 3, all of that divided by h, and my final answer for f of a plus h minus f of a over h is equal to 2a plus h plus 3. Okay. Given the function h of p equals p squared plus 2p, we're just going to plug 4 everywhere there's a p, h of 4. So h of 4 is equal to 4 squared plus 2 times 4. 4 squared is 16, plus 8 is 24. So h of 4 is equal to 24. Given the function h of p is equal to p squared plus 2p, solve for h of p equal to 3. This one's different. This one's not plugging in 3 everywhere there's a p. This is one where I'm going to write this right below this. They're saying that this right here, this h of p, is equal to 3. So I can just take 3 and plug it in right where there's an h of p. So 3 equals p squared plus 2p. We're going to solve for p now. I'm going to set bring the 3 to the other side. And I get 0 equals p squared plus 2p minus 3. Now this is an equation, so I can actually solve this because it's set equal to 0. So p and p, 3 and 1, my sign is positive on the middle term, so my larger term from this has to be positive as well. Set each of these equal to 0. Solve for p. P equals 1. All right. I also go up here and check to see if there's any reason why -3 or 1 would not work in this function. I'm not seeing anything, so your answers are p equal -3 and p equal 1. Express the relationship 2n plus 6p equals 12 as a function of p equals the function of n. So we're just solving for p and replacing the p with f of n, with the function of n. So I'm going to take 2. Oh, okay. Don't know how I did that. Met the magic pen. I don't want to do that. Where's my, hold on. There it goes. Ooh, all right, good. Sorry about that. So 2n plus 6p equal 12. I'm just solving for p, which is what they're telling me to do here. So subtracting 2n from both sides, I get 6p is equal to -2n plus 12. Divide everything by 6. And I get p is equal to -1/3. And I'm reducing. 2 goes into 2 once, 2 goes into 6 3 times. And then plus 2. Now we're going to just where the p is, because everything on the right is now just in the terms of n, this p can become the function of n is equal to -1/3 n plus 2. There we go. Expressing the equation of a circle as a function. So does the equation x squared plus y squared equal 1 represent a function with x as input and y as output? If so, express the relationship as a function y equals f of x. If I do a vertical line test here, that's not going to be a horizontal line test 1-to-1. No. So this can't really represent. I'm going to show you what they're doing here. They're just solving for y because they want everything to be represented as the function of x. All right, we haven't learned about the vertical line test yet. So I'm going to move forward with this to see if this comes out as a function. I can show you how this works in the end. So does the equation x squared plus y squared equal 1 represent a function with x as the input and y as the output? Okay. So solving for y. I'm going to start by moving x squared to the other side. Y squared is equal to -x squared plus 1. And we need to solve for just y. So we have to take the square root of y squared to get y. What you do to one side, you do to the other. Okay. So anytime you take the square root of something, it could be plus or minus over here, right? When you're taking the square root of either side of the equation, you get plus or minus. So this just tells me that the output has 2 answers. It doesn't tell me the input has 2 answers. Would 2 and -2 give me, plugging in 2 or -2 for x, give me different answers for y? No. they're going to give me the same. So this can't be a function. All right. But to finish showing you what this would look like for our representation, you would just take the y and plug in f of x is equal to the square root of negative x squared plus 1. Okay. Let's evaluating and solving a tabular function. Evaluate g of 3. So I'm going to explain to you what I'm thinking about when I'm looking at a table. When I see it says evaluate g of 3. G of 3. First thing I think of is, well, this is the function itself is g of n. So this means when n equals 3, what is g of n? What is the function? That's what I ask myself. So then I come up here and I say, okay, well, here's n right here. Here's where n is 3. What is g of n when n is 3? It's 7. So g of 3 is equal to 7. Let's look at B. B says solve g of n equal to 6. Well, now they're wanting to know what n is. So this type of question is, what is n when g of n equals 6? Well, I come to my g of n and I look for 6. Here's a 6 right here. What is n? 2. So n equals 2. But wait, there's more. Here is another 6 for g of n. And that's a representation of n equals 4. So my final two answers are g of 2, where the n is, equal to 6, and g of 4 equal to 6. Okay. Reading function values from a graph. Evaluate f of 2. So we've got x and f of x, which is also equal to y. Remember that. So they're telling me when I see this f of 2, that means when x is 2, what is f of x? That's what I'm asking myself. Well, here's 2 for x. I go up and find that on my graph, put a cute little dot there, and find out where that's correlating to my y-axis. And that's correlating at 1. So f of 2 is equal to 1. All right. The next one is B. It says solve for f of x. Solve when f of x equals 4. That means what is x when f of x or y is equal to 4? Well, I have to go find on my y-axis 4 right here and put my points on my graph so I can see what I'm looking at here. I've got 2 of them. How does that correspond to x? Well, I just drop them down here to find out where it's hitting on x. The first one is -1. So f of -1 equals 4. But I've got another one right here. So where does that drop down to? 3. So f of 3 also equals 4. Those are my answers. One-to-one function. A one-to-one function is a function in which each output value corresponds to exactly one input value. So we talked about this earlier when we solved to see, is it a function? Every input has to have one and only one output. Well, now for it to be a one-to-one function, yes, each input has to have one and only one output, but also each output has to have one and only one input. Let's look. So determining whether a relationship is a one-to-one function. Is a balance a function of the bank account number? Okay, so the function of bank account number equal to the amount of money in the account. When you go to the bank, you have your own individual account number. No one else has that number, right? So that means that each account will only have $1 amount to it. That is a function. That checks out, all right? The next one, that's A. B, well, is the function of the balance equal to the number, equal to the account number? Well, that just means that, say you have $100 in your account. In order for this to be a function, nobody else in that bank can have $100 exactly in their account. And you can't justify that. You could have more than one person that has the same amount of money in it. And so therefore, the amount of money cannot justify being a function of the amount of money equaling to the account number. So that doesn't work. Finally is a balance, a one-to-one function of the bank account number? No, because both of these would have to have checked out. They had to both work both ways in order for this to be a one-to-one function. So the answer is no for C. Using a vertical line test, we're going to use this to decide whether a function, to decide whether a relation is a function or not. Can be used to determine whether a graph represents a function if we can draw any vertical line that intercepts a graph more than once, then the graph does not define a function. This is the concept with the circle earlier, whenever I was thinking about that, because a circle is not a function. It has one and only one output value. So notice the red line that they drew through here. That shows that, well, it's only crossing at one point. This one is crossing at two, so this is not a function. And then the last one, the ellipse, is crossing at two places as well, not a function. So now we're going to just decide on our own which of the graphs represent a function y equals f of x. The first one here, you can draw a vertical line anywhere along here and only hit one point. So A is a function. B, same thing. It is a function. Now, just because it's a line doesn't mean it's going to be a function. Because what if we had a vertical line? If we drew a straight line through a vertical line, you're going to hit every stinking point on that line. And so a vertical line is not a function. And then the last one we have here is a circle. And if we draw, well, let's see if I can get a straight line as much as I can. It doesn't really matter because I'm going through two stinking points. All right. So not a function. All right. Using the horizontal line test, once we have determined that a graph defines a function, an easy way to determine if it is a one-to-one function is to use a horizontal line test. So vertical for a function, horizontal for one-to-one. So we're going to draw a horizontal line through the graph. And if any horizontal line intersects the graph more than one place, then the graph is not a one-to-one function. So let's look at the first one here. I can draw a stinking straight line through this sucker and hit 3. 1, 2, 3. This is not a one-to-one function. It is a function, but it's not one-to-one. And this one here, I draw a horizontal line through it. I'm only going to hit one point. So this is a one-to-one function. However, a horizontal line, if we had a horizontal line, it would be a function because I could draw a vertical line through it and only hit one point. However, it cannot be a one-to-one function because I can draw a horizontal line through the horizontal line, hit every stinking point on that line, and it's not one-to-one. All right, that's it for 3.1. See you back at 3.2. Let's see if I can end this.